Okay, so now we'll learn about AC analysis in LTSPICE. So let's get started. Okay, schematic. Okay, so now we'll look for the AC analysis for an RC circuit first. So we'll draw an RC circuit. So in AC analysis, the voltage source must be an AC voltage. So now let's give the AC amplitude as 2, and let's give some random values for the resistor and the capacitor. So in order to do the AC analysis, we should move to the simulation command. Now AC analysis, type of sweep that we need. We'll take decade sweep. That is the frequency increases by a factor of 10 in the x-axis. So number of points per decade means from one point to another. If we were to zoom in, how many points we can see. For example, if I were to put number of points per decade as 100, and from 10 to 100, if I were to zoom in, I can get 100 such points. So I'll keep the number of points per decade as 100. Now start frequency, the frequency from where you want to begin the frequency response plot with. It should be a positive value, so we'll give it as 1 hertz. And the stop frequency is usually a large value, so megahertz or maybe gigahertz. We'll give it as 1 gigahertz for now. Okay, so now let's go on. Um, so the blue one is the frequency response of the input source, which is constant as the voltage is constant. So then the green one is the frequency response of the output. Now, in order to find the net frequency response, or to make that is the gain plot, and so it's about percent. So the green one, this is our phase, this is our uh, frequency response. So then we get the net gain of the circuit. So gain remains constant almost up to maybe we can say near 5 kilohertz. The gain remains almost constant. After that it slowly starts decreasing. Okay, now we'll do it for an RL circuit. Okay, give some value for this inductor. For sake of simplicity, we'll give some label over here. Okay, so we'll find straight away find the net frequency response. Yeah. So yeah, so as we can see, the gain increases and then it remains constant at a it remains constant nearly somewhere near 100 kilohertz. It remains almost constant, as we can see. So now we'll look at the frequency response for an series RLC circuit. So let's give one label we have one, as we want to measure the voltage across the inductor and voltage across the capacitor. Sorry. Let's give some values to the inductor and the capacitor. Okay, so now this is our series RLC circuit. Now let's see the frequency response. So if I were to click at V of 1, this is how the frequency response looks like. As you may be knowing about this, the right side is the phase plot and the left side is the gain plot. So, this is frequency. That is for V out. Of course, V out 1. Now let's take the case of V out 2. Okay, now again let's divide by V in here. So yeah. For V out 2, it's same as that of a low pass filter. Frequency means, so the gain remains almost constant there. So when you're 10 kilohertz, it remains almost constant. After that, it starts decreasing drastically. Okay, so this is the case of a series RLC. Now let's do for parallel RLC. Giving some random values again. So the frequency. So as the voltage across the resistor, capacitor, and the inductors V in itself, this will be the frequency response. That is the gap. The gain remains constant as the output voltage. The gain remains constant for all frequencies. So, this was for a parallel RLC. Now we'll study about for an inverting amplifier. So, let's take an amp. It is 747. Okay. Let's put a label for the output voltage as P out. Uh, yeah, we need to give voltage supply to the op-amp as well. So yeah, we should call these as well. Let's give some values to the resistors as 1k, and we'll give the other resistor as 10k. And AC voltage source is 2. So that frequency response B. So yeah, second, that of a low pass filter, the gain remains constant up to almost 10 kilo, means somewhere around near 20 kilohertz. After it starts decreasing drastically. So now we'll also study about frequency response for a non-inverting amplifier. Okay, so yeah, let's put a label here. So yeah, again we get a low pass filter, and yeah, gain remains almost constant up to somewhere around 15 kilohertz. After that starts decreasing very fast. So this was a frequency response for a non-inverting amplifier. Now we'll do the AC analysis for a differentiator. So this is the circuit of a differentiator, and so the frequency response will be yeah, like this. This is the phase plot. So yeah, it reaches a peak at nearly 29.4 kilohertz in this case. So it's like as we can see, the gain first increases, and after that it decreases, and at very high frequencies it's almost constant. So this was for the case of a differentiator. Now we'll try to study the frequency response for an integrator. So let's make a circuit of an integrator. We just swap the resistor and the capacitor. That's all that we need to do. Okay, so oops, source doesn't matter. Okay, let's give 1 kilo ohm and 100 nanofarad like before. Okay, so now let's plot the frequency response divided by V. Yeah, So this is a frequency response. So gain increases, and somewhere near 10 kilohertz it's almost constant the gain, as you can see it. And then on the phase plot, and we have phase plot is like you can see full phase plot. So that's it for now.